5 billion years from now, the sun is going to die. That part isn't new information. What is new is this: it won't go quietly. According to a study presented this month by a theoretical astrophysicist at Caltech, dying stars like our own sun don't drift peacefully into their final form. They spend their last few 100,000 years getting violently, repeatedly kicked thousands of times by nothing more than their own dying breath. Here's the part of a star's death everyone already knew. When a star roughly the size of our sun runs out of hydrogen fuel in its core, that core contracts, and the star's outer layers respond by ballooning outward, sometimes swelling to nearly 100 times the star's original size. This bloated, unstable phase is called the red giant stage. Over time, that puffed-up outer material gradually escapes into space entirely, eventually leaving behind nothing but a small, dense, slowly cooling stellar core called a white dwarf, one of the most common types of stellar remnant anywhere in the universe, since this is how the overwhelming majority of stars eventually end their lives. This has always been treated as a relatively calm, symmetric process, mass simply drifting away in every direction roughly equally, until the star settles quietly into its final form. Jim Fuller, a theoretical astrophysicist at Caltech, built a new model suggesting that picture is missing something essential. Motion. According to Fuller, the mass isn't actually lost evenly at all. Instead, blobs of plasma erupt chaotically from the star's bloated, churning surface, in a messy, asymmetric, unpredictable pattern, more like a pot boiling over unevenly on one side than a balloon slowly and uniformly deflating. And every single one of those uneven ejections comes with a consequence baked directly into basic Newtonian physics. Fuller put it plainly: blobs of matter are chaotically ejected from the surface of these bloated stars in an asymmetric fashion. And every time that happens, the star gets a small kick in the opposite direction, exactly the way Newton's third law predicts for every action: an equal and opposite reaction. One single kick on its own is almost nothing. According to Fuller's calculations, each individual recoil moves the dying star at a pace of only a few meters per second, slower than a casual human jog down the street. That's easy enough to dismiss as background noise. The problem is that a red giant doesn't experience just one of these kicks, or even a handful. It experiences roughly 10,000 of them, scattered across its final few 100,000 years of existence, each one launched in some random, unpredictable direction as the next chaotic blob of plasma escapes from a different, unpredictable point on its surface. Here's why that specific number matters more than it first appears to. If those 10,000 kicks were all pushing in completely random, independent directions, you might reasonably expect them to simply cancel each other out on average, leaving the star more or less exactly where it started. That's not what happens. This is what mathematicians call a random walk, and the same basic principle shows up in a very simple, familiar example. Imagine flipping a coin over and over, moving one step north on heads and one step south on tails. Even though every single flip is completely random and unpredictable on its own, after enough flips, you become extremely unlikely to land back exactly where you began. You end up displaced purely by the accumulated statistics of pure chance, even though no individual step was ever aimed anywhere in particular. Run that same math across 10,000 stellar kicks, and Fuller's calculations show the dying star ends up drifting through space at a genuinely respectable clip, roughly 1 kilometer per second, about 2,200 miles per hour. A permanent, accidental parting gift quietly inherited from its own chaotic death throes. This isn't just an interesting new detail bolted onto an old, familiar story. It directly explains a specific puzzle that had been quietly bothering astronomers for years, without a clean physical explanation behind it. Karim El-Badry, also at Caltech, had previously noticed something strange while studying binary star systems. Pairs of stars gravitationally bound together, sometimes separated by enormous distances. Wide, loosely bound binary pairs become noticeably rarer, specifically once one of the two stars finishes its transformation into a white dwarf. Almost as if something were quietly working to pry these distant partners apart the moment that transformation completed. Fuller's kicks provide exactly that missing mechanism. If a newly formed white dwarf's accumulated kick speed ends up faster than the gentle orbital speed, holding a wide binary pair together in the first place, that kick alone is more than enough to break the pair apart entirely, sending two stars that once shared a system drifting off onto permanently separate paths through the galaxy. El-Badry himself responded to Fuller's model with clear professional relief, saying he was pleased to finally see a physical explanation for an observation that had personally puzzled him for several years. That's the kind of quiet, understated satisfaction that tends to show up when a genuinely nagging astronomical mystery finally clicks cleanly into place after sitting unresolved for a long time. Fuller's model doesn't stop at simply explaining why some binary systems drift apart, either. It also makes a specific, testable prediction about systems that don't have room to safely drift apart in the first place. In binary systems, where the two stars already orbit closer together, the same repeated kicks could, instead of separating the pair, gradually nudge their orbits closer and closer together over time, eventually driving the two stars into an outright collision. A collision like that wouldn't be quiet either. Fuller suggests it could trigger a genuine stellar explosion or some other kind of bright, detectable transient event. Precisely the kind of signature astronomers could specifically search for in existing survey data going forward, to test whether this entire kick model actually holds up under real observational scrutiny, rather than remaining purely theoretical. This isn't even the first time astronomers have suspected white dwarfs get some kind of birth kick. Decades ago, Hubble observations of the ancient globular cluster NGC 6397 found young white dwarfs sitting unexpectedly far from the cluster's dense core. When astronomers had assumed the most massive stars, the ones destined to become white dwarfs, should cluster tightly near the center instead. That older evidence pointed towards some kind of kick happening, without ever fully explaining exactly what was causing it. Fuller's model is the first to connect that decades-old observational puzzle directly to a specific, calculable physical mechanism, rather than leaving it as an unexplained pattern in the data. There's an uncomfortable, deeply personal detail buried inside all of this math. Our own sun is going to follow this exact same path. In roughly 5 billion years, it will swell into a red giant large enough to reach out toward the orbit of Mars, very likely engulfing Mercury, Venus, and Earth itself along the way, long before any of this kicking begins in earnest. Only after that dramatic expansion, during the star's final few 100,000 years, will the sun begin experiencing its own share of Fuller's 10,000 chaotic, asymmetric little kicks, quietly drifting off in some direction nobody can currently predict, propelled by nothing more than its own uneven, dying breath. Stars have never been the calm, static points of light they appear to be from Earth. They're born in violence. They spend billions of years continuously fighting their own gravity just to stay stable. And now, it turns out, Even their slow, ordinary deaths come with one final, chaotic kick after another, thousands of times over, until the star that once anchored an entire solar system simply isn't sitting where it used to be anymore. Beyond the visible, beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel, new episodes on space, physics, and the edges of what we understand, with new content going up every day.